This is pi, bonding. But what is the symmetry of this? G or U? U, because they will, this reflects onto this but comes onto a negative. Therefore, the function becomes negative when you do an inversion. So the pi bonding orbital actually is U symmetry. That's the reason I put U there. But supposing it is the other way. And they get close to each other. What do you think will happen? They got to look at each other. Plus can reflect onto a plus, minus can reflect onto a minus, and therefore this particular shape of the orbital will actually give rise to G symmetry. So that's the reason why pi star orbital is of G symmetry, pi orbital is of U symmetry. When it comes to sigma, the bonding orbital is of G symmetry, and the anti-bonding orbital is of U symmetry. Okay. So this is basically our electron configuration. We don't have to worry about this part at all because they are completely filled. And we have seen even in atoms, if they are completely filled, those really don't contribute to your term states. If I am going to do the configuration for ion, I don't have to worry about all the electrons which sort of throws up the shells up to about R count. It's only the valence electrons that are left in open shells that I really need to worry about. So I don't worry about any of these because since they are all completely paired, they will actually give rise to no angular momentum issues when I am looking at the term state. I need to worry about this. When I worry about this, what's the configuration I am really looking at? Pi, U, 3 and sigma G, 1. These are the two orbitals I really need to take into account to get my term state. How many electrons can sit in pi U totally? 4. I am having 3. So what is this pi U3 looking like? Pi U1. You remember we said if I have p orbitals, if I have 5 electrons in p orbitals, don't take all these 5 electrons and start building up a term state. The p5 is the same as p1, the whole formalism. And therefore pi U3 is actually the same as pi U1 with some differences, but otherwise as far as building up term states are concerned, pi U3 is the same as pi U1. So this is the same as pi U1 sigma G1. This makes life a lot easier. We don't have to worry about 4 electrons to build up our term state. We only have to worry about 2 electrons. Now how do I do it? If I say pi, what's the lambda value for that? Plus minus 1. Right? So this fellow has plus minus 1. This is lambda 1. Just like we have L1 and L2, we're going to have lambda 1 and lambda 2. For this, what is lambda going to be? 0. And only 0, there is no plus minus 0. So there is only 1 0. So this and this together, if I add them, and they are going to already components, there is no big vector addition, I am only adding components actually. So plus 1 and 0 will give me the lambda value. This will give me the lambda value. How much is that going to be? Plus 1. And what is the other one going to be? Minus 1 and a 0 will give me minus 1. But what does plus 1 and minus 1 taken together mean? It's a pi state. Therefore, these two together will actually give me, actually when you write the print, it's easy. In fact, what we do is, this and this must be different. You write this with small pi, something like that. Whereas here you write like a capital pi. That's the term state. It's the same as writing a little p for the orbital and a capital P for your term state. So a little pi for the orbital and a capital pi for your term state. So the three together will give me a pi state. I have got that fixed now. What about the spin? There are 2 electrons. So what are the possibilities? There are 2 different electrons, right? They are not same. They are not equivalent electrons. One is sitting in a pi orbital, other one is sitting in a sigma orbital. Non-equivalent electrons. You don't have to wake Pauli up from his grave. Let him lie there. You don't have to worry about it. So when you have 2 electrons this way, what are the possibilities? Triplet and a singlet. So I can basically have triplet pi state or singlet pi state. Both are possible. One more thing to be fixed up, and what is that? The U or the G symmetry. U into G is what? Always U. U into U is G, G into G is G, and U into G and G into U both will give me U. There's no complicated signs in this. You know, it's plus into minus, minus into minus, plus into plus, and so on. That's it. So this is going to give me a U state. Therefore, I'm going to have term states that result from this configuration to be triplet by U and singlet by U. That's it. Any questions? We do the next one. And the next one is 2p pi u3 and 2p pi g1, which means it actually must be 2p pi c star now. But then if I say pi g, you know it must be a star. So I have therefore 2p pi u 3 and 2p pi g 1. Again follow the same path. 2p pi u the same as pi u 1. So this is the same as pi 1. And this is, so it's pi 1 type situation. So how do I do this now? So lambda 1 is plus minus 1, that is for this electron, and lambda 2 can be also plus minus 1. So now how do I have to take all combinations? So I take lambda 1, lambda 2, plus 1, minus 1, plus 1, plus 1. Keeping this constant, I have run through the two possibilities for lambda 2. Now what do I do? Take this minus 1 and again run through the two combinations. So what's the value of lambda? This is going to be 0. What is this going to be? 2, minus 2 and 0. Taken together, what is it telling you actually? I have a delta state. What does this mean? 0, the sigma state. And I have one more 0. And in case of sigma, however many zeros you get, that many sigma states are there. So therefore, I have two sigma states possible. The sigma states are non-degenerate. I can't take these two together and say it's one sigma state. So that means I am having a double degeneracy in a state. But I know sigma states are non-degenerate. So that 0 would give me one sigma state, this 0 would give me another sigma state. Which means this configuration actually gives me one delta state and two sigma states. And what about the spin on this? Again, it can be both triplet as well as singlet, because I basically have two non-equivalent electrons. So this can be triplet, singlet delta, triplet sigma, singlet sigma, and another triplet sigma, another singlet sigma. So I have 6 states that come out of this situation. Now how many, and what is the symmetry of these states? It's U into G, therefore it has to be a U. So if you're given these electronic configurations, you basically have to figure out what the little lambda value is and run through all possible combinations. And keep in mind, while in atoms, when I gave you L equal to 1, it was L plus 1, 0 or minus 1, because I was not giving you the projection on any axis, I was giving you the angular momentum vector. In the case of molecules, homonuclear diatomic molecules, or even heteronuclear diatomic molecules, in diatomic molecules, when I give you lambda, it's a projection on the internuclear axis. And therefore, if pi, there is only plus 1 minus 1, there is no 0 to it. Delta plus 2 minus 2. That is where this is slightly different from the way you dealt with in atoms. In atoms, you have to go through all possible ml values for a given L value. L value was given to you. You have to get the ml value. Here, the projection is given to you. So when I say it's a pi orbital, it's got projections of plus 1 and minus 1. No 0. 0 is reserved for the sigma state, sigma orbital. Okay. And then you run through all possible combinations, and then whatever you get is what you get. So, in fact, what I would suggest you to do is to, make your own possibilities. So run through, take the electron, put it somewhere else and see what you get, and sort of practice yourself into getting different states. Except that don't take two electrons in the same state. So then it comes to an equivalent situation. And I haven't taught you how to do equivalent situations, because then you have to apply the Pauli exclusion principle for molecular states, which is not something that we have learned at this point in time. So we are dealing with non-equivalent states and try to take different combinations of non-equivalent orbitals and then figure out what these term states should be. Rest assured, there will be something on term state for molecules. What I will do is I will do the fourth one, and I think that takes care of assignment 4, and we will stop at that point. Tomorrow we will do 5, and maybe on Wednesday we will do 6. Take problem number 4, and what I have given is problem number 4. Problem number 4 is rather simple, excepting that you must know how to draw the diagram and label all the quantities given to you into that potential energy diagram. If you know how to do that, it's pretty straightforward. What I'm saying is, iron has a dissociation energy D0 in the ground state of 12,000 electrons. Again, these are all real numbers. So I'm taking the iron molecule, and I'm saying the dissociation energy D0. If it is D0, how do I label that? B equal to 0. Right? If I went from here, what would that be? That's D. But then, in real life, when you do an experiment, molecules are in B equal to 0 state. No molecule is ever sitting here. Therefore, D is sort of a number that spectroscopists always get. But in real life, when you were to measure the dissociation energy, you're always measuring D0. Because molecules are sitting in B equal to 0. And then you tear them apart into atoms. And you're using that much of energy to do so. So D0 is 12,000 wave numbers for the iron atom in the ground state. In this electronic state, the molecule dissociates into two ground state atoms of iodine, which is namely WP3 and WP3. What do I mean by that? I simply mean that if I have this iodine molecule, and I tear these two atoms apart and get two atoms as dissociation, the two atoms are ground state, are iodine atoms. Now, what is the term state for iodine? It's a P5 configuration, right? If it's a P5 configuration, it's the same like a P1 configuration. And if it's a P1 configuration, what should it be? Doublet P. That's why we have doublet P. And then it can be doublet P 1/2 or doublet P 3/2. But iodine is more than half full, P5. Therefore, doublet P 3/2 has to be the ground state. So when I take this molecule, which is iodine, I2, and I yank it out, and I produce two atoms, one in the right hand, one in the left hand, each of these iodine atoms will be in their respective atomic term states. And I am saying here that the ground state, if I took the iodine molecule in the ground state and I pulled it apart, then I would get two iodine atoms in their ground states. And what's the ground state for the iodine atoms? Doublet P 3/2. Right? So this essentially is telling you, ground state molecule, yank it, this is what you will get. But supposing I take this iodine atom into an excited state, which is what the next part of the question is. And what does it say? Iodine allow transition to the B state, and in the B electronic state, the molecule dissociates into one ground state atom and another one into an excited state atom. So which means the B state, which you saw earlier, was shifted relative to the ground state, I think the 3.06 or whatever. So I take a molecule of iodine, which is sitting in the B state, which means I have made some changes to the electronic structure of iodine. It's now sitting in the B state. And in the B state, if I yank it out, I have two iodine atoms. And I look at these two iodine atoms, what would I have? I won't have one ground state and another ground state. It actually turns out to be one ground state iodine atom and one excited state iodine atom. Therefore, I have iodine what is this 3/2 and 1/2? That's a spin orbit splitting. Because it's the L and S coupling to give me J, and and they couple one way to give me 3/2 and one way to give me half, there's a spin orbit states. And we know in ID, WP 3/2 is lower in energy than WP 1/2. That's the reason why WP 3/2 and WP 3/2 together will be lower in energy than WP 3/2 and WP 1/2. Because this one is actually bringing the energy up there. So I have drawn a diagram. Now let's see if I can fill it out. The frequency nu00 of the H to B transition is 15,000 wave number. What do I mean by that? I simply mean going from here to here, 0, P0 to V0, and it is always labeled as nu00. And I am saying that that transition actually has a frequency of. In this question, basically what you have to do is draw the potential energy diagram and fill in energy information and other information that I have given you, and then see whether you can reduce information that is being asked of you. So already we filled up 12,000. We filled up the states that is coming out. We filled out what the nu00 is, and let's see if there's anything more for us to give. Yeah, the energy of the WP half state of ID is 7600 wave numbers more than WP 3/2, which means in the iron atom, WP 3/2 and WP 1/2, this distance is actually 7600 wave numbers. This information is given here, and how do we know this? We know this from atomic spectroscopy. If you take iron atom and do spectroscopy on it, you will know that this difference actually turns out to be 7600 wave numbers. Where does this information come in there? Where do I put it in there? Now this difference here is actually the difference between WP 3/2 and WP 1/2, and therefore this must really